variation. This is going to be 3.5. Variation in multivariable functions. Okay, like I said, you've seen this before. They're using a little bit different terminology than I've said before in a past class, but what you're going to see is this. Okay, I'm going to just give you an example of one. And these are nice ones because remember, they're the ones, if you look at them, if you kind of go back to intermediate algebra, they're the ones that when you read them, they tell you exactly what the formula is as you read them. Okay, so notice this one says that y varies directly. So this is a direct variation. As one variable gets large, the other variable gets large with it. Or it'll say is proportional to the nth power of x. Okay, we call this a constant of proportionality, and that's why they're using the k. Okay, k is known as a constant of variation. Okay, so I always think of this one like, I notice it says y, but they may give you any other variable. You don't know what kind of variable they're going to give you, or description of something. Okay, and so you can apply your own variable to it. But then whenever I see the words varies directly, I automatically always put an equals k. And then I put down on whatever's the other on the other side. Okay. So notice this first one here. The distance that a free falling object falls, is directly proportional to the square of the time it falls before hitting the ground. So notice, let's just kind of parse out that information, just kind of see if we can't find the formula. The distance. Well, let's talk, there's my variable, however you want to put it, but that's going to be the distance that a free falling object falls is directly proportional. That's going to be an equals k, and I'm going to be doing multiplication. Proportional to what? The square of the time it falls. And so notice that I'm just going to put t squared. And there's my formula. And now what they're going to do now, the difference between this one and what you've done before, sometimes, so watch out, be real careful on these. Sometimes on some of these, they're always going to make you solve for k. But then they may go ahead and start giving you other things. You might just solve for things. Okay, do some algebraic steps. So just kind of watch out for that. This one, they're going to make us just solve for k, and then they're going to give us some new numbers. So they're going to say, if an object fell 46 feet, well, notice my distance is going to be 46 feet. In 3 seconds, so my time is equal to 3. How far will it have fallen in 5 seconds? Well, I don't know because I don't know the k value yet. But I can find k by plugging everything into my formula. So I'm going to come right in here and go, okay, I've got 46 is equal to k times 3 squared. Let's divide off the 3 squared off both sides. Be very careful with these answers because look at that right here. It says round your answer to the nearest integer if necessary. If I get a k value of 46 over 9. That would reduce down. Okay. No, that wouldn't reduce. Sorry, that won't reduce. You can put it in a decimal if you want. Just make sure you go to decimal, go to the 10th place since you're going to go to the nearest integer. Okay. But now notice I have a k value. So now I can plug in something different. They say, hey, how far will it have fallen in 5 seconds? Well, I don't know. Let's put everything in. And notice I have a d that's equal to now 46 over 9 times how many seconds? 5 squared. And when I do the math to that, very simply in my calculator, I get 127.7 or 128 feet. And so there's my final answer right here. Concise and quick, correct? Not a lot of fluff. We good on that one? Yeah. Now remember, for direct variation, just so you can know conceptually, remember, as one thing gets large, the other thing got large with this one, right? Okay. As the time increased, what else increased? The distance it fell. The larger the thing was, the longer it took to fall. Okay, there is a direct proportionality. You're going to hear this in the news a lot. That's something I'm really kind of hanging out on. Is you're going to hear things, especially in the news, all the time. They're going to say something the president did is directly proportional to how these people feel. Okay, or the amount of money taxes you pay is directly proportional to how broke you are. Okay, that kind of makes sense. Okay. Well, if you have direct proportionality, you can also have what we call inverse proportions or inverse variation. Seen this before? We say something varies inversely. Okay, we say y varies inversely or is inversely proportional to nth power of x if there is a non-zero constant k. When you see inverse, just think division. Okay? Remember on the last one, we were multiplying. As one thing got large, the other thing got large. The only way that's going to happen is when you're multiplying something. If when things get smaller, start dividing things. Okay, so inverse says divide. And once again, you can literally just start plugging things in. So once again, let's do this example here. Suppose that y, once again, it's going to give you some variable. This was giving us a direct variable. It's saying a y. Y is inversely proportional. Okay, that immediately I automatically write the equals k and then put a division symbol to the cube of x. Oh, okay, cube of x. And now you have, very simply, a formula. So they're going to say, hey, when y is 16, okay, well, let's put a 16 here. And when x is 6, what is y when x is 14? Well, we don't know yet because we don't have that constant yet, do we? So let's take a look at that. We got an equals k here. And then we got a y, then we got a cube root of 6. Well, I got to get that k by itself, which means I'm just going to let me change colors here because I really don't like using green. It's weird. I'm going to multiply up, right? Simple math here. And then I get a k that's equal to, well, how about 16 root 6? And I'm sorry, I did some math. That's the cube root. I was doing a square root. Make sure you do a cube root. I'm keeping it in this form. Now, you don't have to. Okay, if you end up working at the math of this one, it ends up being a 29.0739. Well, and so on and so forth. It's an irrational number. It's going to keep going. And the reason I did that is because, look here. Round your answer to 2 decimal places if necessary. Remember, if it says round your answer to 2 decimal places, do all your calculations to 3 and then round back. Okay? Because if you can't round to 2 decimal places if you just go to 2. Okay? Because you've cut it off right there. You got to go to 3 or else you're going to be getting those red bars and not know why. That's why right there. Okay? Now on a midterm, I'm going to give you like, hey, I get what you did there. You're going to get some pretty high marks on it still, but that's really elementary math right there. Okay, go to 3. Get used to that. Especially if you're going to statistics. Statistics, I am very picky about rounding. We have what we call rounding rules. Okay, you have to do this. Okay, it's not hard. You just gotta know. Hey, if it's 3, go to 4. If it's 4, go to 5. Okay, when you're doing your calculations. Okay, so notice you come in here and they go, hey, well, what about whenever x is 14? Well, what's that going to be for y? I don't know, but I do know that I can put all this back together and go, well, how about y? Oops. How about y is equal to well, I'm going to put this in decimal form. I got 29.0739 divided by the cube root of 14. When I do the math of that, I end up getting 12.06. And that's after doing the math and go ahead and rounding. And that's all she wrote on that one. And realize once again, I just read the problem and did exactly what it said. When I saw inverse, I'm dividing. When I see directly proportional, I'm multiplying. Okay. This is inverse proportionality. As one thing gets large, the other thing's going to get small. Okay. So the larger x gets, okay, the larger it gets, the smaller y is going to get. Kind of makes sense. If you really think about it, when something doesn't make sense because of the variables, throw some numbers in. Because really, look at it this way. If 1 and 1, that just equals 1, right? Think about it, we're doing this. We're doing 1 over x. We'll just do a y here. Y is equal to 1 over x. As x gets large, what's happening to y? It should be getting smaller. Well, when x is 1, y is 1. But what happens whenever you get y is equal to 1/2? Well, notice what's happening here. What happened? X went up. X went to 2. But what's going to happen to y? Well, it's now 1/2. It's 0.5. It actually dropped. Notice what's going to happen. You put a 3. Now you're going to 1/3. That's 33% or 0.33. As one's getting larger, the other is getting smaller. But multiplication doesn't work that way. Multiplication for the direct variation is saying, as one gets large, the other one's going to get large proportional to whatever that k is. Okay, does that make sense? Because 1 times 1 is 1. Well, 1 got large, y got large with it. 1 times 2, well, that's 2, and 2. So notice they're going up. Okay. Difference being is that k value. How steep is your line? Make a slope. How steep? Is it going to go up fast? Is it going to go up slow? Okay, so. In your notes, I kind of show the graph to it a little bit. Joint variation. They're just giving you a couple more. Okay? We say Z varies jointly. Okay? Jointly. Notice it still equals K. Okay? They're saying jointly because now you're dealing with more than one variable. Okay? To the nth power of x to the nth power of y. They could make that more difficult to say. And once again, K has to be non-zero. So look at this one. The lift, once again, read it, just read it straight across carefully. The lifting force, F, exerted on an airplane wing varies jointly as the area, A, of the wing surface, and that little and says, hey, better keep going because I've got more variables to give you, and the square of the plane's velocity. Okay, so we can write this as, well, F equal to K again, always that constant. There is some constant, there is some universal constant working in the background to make sure everything always works. Okay, and then we've got area. It tells me, hey, area. And then what am I multiplying by? The velocity. What? What does it say?
Square.
Square, exactly. The square of the velocity. You possible future physics students. Okay, if you want to take it out here. First off, the math in this class is way harder than the math you take in your physics class. If you ever want to take Professor Kieran's physics class, I'd suggest taking it. It's pretty awesome. And he's an awesome teacher. He will make sure you pass as long as you do the work. He wants you to pass. You will never find a professor more happy. Okay. But can you tell me the difference between, just kind of real quick, you've taken plenty of math classes. What's the difference between speed and velocity? Why didn't I use speed? Speed says this. I'm in my car. I ask you, hey, how fast your car go? And she says, top speed in my car. Do you have a super nice car? More or less? Fast-ish? Probably governed though, isn't it? Problem.
Probably
Say-
would hit 110.
There you go. Most of us just said, probably hit about 110. Okay, that's speed. That's as simple as that, right? So if someone says, hey, the speed of my car is 110 miles an hour, they just told you speed. Velocity is this. Here's the difference. Here's the only difference. My car went 110 miles per hour north.
Direction?
It's speed with direction. That's the only difference. Okay, why are they telling us velocity on this one? Because a plane is probably flying a direction. We just don't know the direction, but it could, and it's denoted by literally a line on a graph with a little arrow on it. It'll say, hey, and the longer the line is, the greater the magnitude, but that gets into whole area of math, but it's how we say how fast things are. But we not only know how fast they're going, but where they're going. Okay, so that's a little bit of just like a little side note, because I want you to walk out knowing stuff. If someone goes, what is velocity? Oh, just say speed with direction. That's it. So notice they're going to give me some information now. They said the lift of a wing with an area of, oh, here we are, 160 square feet, okay, is 11,900 pounds when the plane is going 200 miles per hour. Okay, well, we can put all this information in, can't we? Can't we just come in here and go, well, this is going to equal 11,900 because there's my force. Equals K multiplied by, well, the area they give me is 160 square feet. And they say at 200 pounds. Right? Well, can't I just take all of this right here and divide that off, right? That cancels all that out. And then I'm going to get a K value that's extremely small. I get K is equal to 0.001859375. Now, let me tell you something, just real quick. A lot of your Hawk stuff, and please don't blame me, that says round to the nearest integer right there. Very plain as day, you can all read just fine. But realize you can't just put in 0, and you can't put in 0. Now you could round this to a 3 or to a 2, right? Okay. A lot of the calculations you're going to see done in Hawks, they're just using everything that's in the calculator. They just don't erase the K value. Okay. If you're doing your review and you see one like that, and you're like, why am I not getting the same answer as what's on the review sheet? It's because that's the K value I got in my calculator. And so I'm using just the whole K value. You don't have to do that if you don't want to. Hawk should still give you the correct answer, even if you just round to 3 decimal places on this one. Because eventually what you're only going to round to is what? The nearest integer. So that is so far beyond, you're at 1/1000th, okay, at that point. So don't freak out about it too much. Even on your assessment, or on your midterm, I have a variation of like, if you rounded to here, this should be your answer. If you use the whole calculator, this should be your answer. And so I use the gamut of any number in between there, okay? So don't freak out on it too much. Does that kind of help you out a little bit? Especially when you're dealing with variations into large decimals, you can get some variation there. But that's our constant. This is a constant. Well, it may be an ugly constant, but it is a constant nonetheless. So let's come in here very quickly and let's say, okay, find the lifting force if you're going 230 miles an hour. Oh, well, look at it, huh? Notice they didn't change the plane. So you still have the same area. That's why they're still using the 160. So, well, what's the lifting force of that? F is equal to that. My K value is all of that. I'm going to write this as a red K right here. We'll change this into a red K. The reason I do this is because more than likely how I'd be working this question, the K is still in my calculator waiting on me. Okay? times the 160 again, because it's the same plane. It's just now going what? Faster. How much faster? Well, now it's going 230 miles per hour. But what's the problem with that? What did I not do?
Square it.
Square it. Don't forget to square it. I did that for a reason. People forget the original formula and they forget the squaring. Okay, so always check your original formula, make sure you did everything correct. Okay. So notice whenever you do all of the math to this, okay, you should get, when you round it, 15,738 pounds. A little crappy plane. Okay, that is not a whale. Ironically, I was an artist for 25 years. I'm actually a pretty good artist. This is just hard to draw. Okay. That is the force pushing up. Right there on that wing. 15,000 pounds are pressing up on that wing. So you can imagine next time you're at a plane, look out the wing. First off, it wouldn't be hard to find the area, you can Google. And then you can say most planes, like the last time I flew to Austin about 4 weeks ago, and those planes go about 539 miles per hour. So it's not unheard of to literally have hundreds of thousands of pounds of air pushing against the bottom of that wing, and yet it's just there. So, yeah, it's kind of interesting whenever you actually see the numbers behind it and realize that's just aluminum. Okay. Let's do what else? Multivariable functions. Okay. Do not believe one of these is on your multivariable functions are a little bit weird. Okay, you've heard of a function. Okay, let me just kind of write a function real fast, okay? You can have a function of m of x. Can we all agree? That's just a function. That's how does m relate to x, right? That's all that's been happening, right? We've had functions, okay? Well, this multivariable function that we're going to start dealing with here is saying, hey, I'm going to give you a function, but I need you to start plugging things in two different places. Watch how this is going to work. Read it carefully. The mass varies directly. Okay, so we have to start reading that very carefully. The mass, m, is equal to k. Nice, huh? As the kinetic energy, they give you what? The new variable they want you to use. And yes, use their variables. These are actual variables that would be used in a physics class, okay? There is a big K, there is a small k. But notice they kept going, and inversely. Oh, that means that inversely means I'm going to put what?
Division.
A division line. And inversely as the square of the velocity, big V. Okay. It's going to say to you eventually, probably in your homework, write this as a multivariable, okay, function. This is how it looks, and then we're going to go in and solve, okay? You're going to need to go ahead and find your K value first, okay? So let's go and find K, because they're going to give us enough information to find the K value, right? So if the kinetic energy is 28, so we've got this M is equal to K times 28 joules, and the velocity is 2 meters per second. Okay, well, that just turns into what? 2 meters per second, but I've got to do what? 2 what?
Squared.
Squared. Exactly. Okay. Well, then I've got to come in here and go ahead and do the math. And then the mass is 14 grams. So they're going to give us the mass as well. Okay. So notice they're going to say the mass is 14. So 14 is equal to K times 28. And then 2 squared is 4. Good with that? Got to get K by itself again. So how about we come in here and we've got 14 times 4 divided by 28. Can we all agree that's what K would equal? To do the math of that, should get 2. We want to double check my math on that, make sure I'm right. Times 4 divided by 28, looks like it's gonna be right. Yeah. So the K value is simple, isn't it? K is just going to equal 2. Now, express the mass. Express mass as a function of kinetic energy and velocity. Did they give you a K value? We do. We have one now, right? K value is what? That's our constant. Could I rewrite this whole formula with that K value? Now, notice they didn't give me anything else. We're not solving for anything else now. Can I go ahead and write this whole formula out this way? How about 2K velocity squared? That make sense? Now, if I give you a K value and I give you a velocity, if I give you the kinetic energy and I give you the velocity, could you find my mass? Yeah. Well, this is a multivariable function. We're saying, and that's what it's saying right here, express the mass as a function of velocity and the kinetic energy. Isn't that what a function says? It says, hey, f of x says what? Give me an x. You plug that x in everywhere in the formula, and then what am I going to pop out the back end? Some y. This one is saying, hey, if you want to find the mass, you can't just give me one variable. You got to give me 2. You need to give me the kinetic and the velocity. So I have a function with relation to K and B. And that is the mass as a function of kinetic energy and velocity. And now notice if you gave me either one, both of those, I can plug them both in and give you the mass. That's all you just did. We won't be dealing with these a lot. If you deal with these, you're going to solve. You're never going to have to deal with functions like this until you get to like calculus 3. Okay? Because when you start dealing with functions like that, you're getting into, I mean, it's a little bit harder, obviously, because things are going to get a lot more complicated. And you can actually add on. Multivariable functions can get really large. Okay, like this right here would be a 2D plane. Okay, but I could add 3 functions. Okay, not only am I going to have an x coordinate, a y coordinate, but I could also have a z coordinate. Well, now you're dealing with 3D space. You can also go into the 4th dimensions, 5th dimensions. Okay, but that's how that works. Good on that? All right, there you go. There's 3.5. 3.6, super easy. Not going to get into that one. Okay, honestly. I've got a couple examples in your notes. 3.6 has got a couple of word problems on there. They're like, I said, one of them's got 3 parts, super simple. Okay, I want to get into 4.1 today so that we have a chance to start getting ahead because 4.1, 4.2, and 4.3 are due next week. Any questions over chapter 3 at all? Very kind of good. Now remember on 3.3, do not forget, you have all of those new functions you learned about in 3.3. They are all over. I remember those? Like power functions, piecewise functions, all that stuff. Okay? You got to go and start studying those ASAP because you're going to be tested over those. Okay. And we're going to see them again today. Let's take a look. But FYI, as of right now, that's everything that's going to be on your midterm. Okay? 1 through 3 is your midterm. Or 1. Transformations of functions. Now we're going to get away from base functions, and you're going to start learning how to move them up and down, left and right, squish them, turn them, flip them, or just to be able to notice that's what happened to them. Now, let me tell you now, the better you know your base functions, what you learned in 3.3, the easier this is, okay? If you can know what the base function is, like you all know what x squared is, that's a parabola, right? Okay, we all know x to the power of 1 is just a line. But remember, what is the x to the power of 3? Remember, it's the little weird line that does this. How about a cube root? It does this. Okay? If you can kind of remember that, I do promise you, chapter 4 is going to be a lot easier. Okay? It's going to look messy, but for me, especially whenever I start teaching about what we call even and odd functions, for some reason, people get disconnected on that, and I literally go, picture the graph. If you can picture the graph, you can go, oh, I know exactly what it is. No matter what. No matter how ugly it looks, you can go, I know. Because of what the base function is, what the degree of the polynomial is. Okay, remember that's the base function. That degree of that polynomial will tell you roughly what that function looks like. Okay, so let's look at this first one here. We're going to do some horizontal shifting. Let f of x be a function, let h be a fixed real number. If we replace x with x minus h, we obtain a new function g of x, okay, which is equal to f of x minus h. The graph of g has the same shape as the graph of f, but shifted h units to the right if h is greater than 0, and shifted absolute value of h units to the left if h is less than 0. Why do they put absolute value? Because you can't have a distance with, okay, we're going distances here, okay? Realize they give you a formula. I'm going to help you this in 2 ways. One, they give you a formula here that says this, hey, there's my formula, f x minus h, okay? Notice this plus 2 here. Okay, realize what that's saying right there. Okay, that plus 2. You know what that's telling me? Why is this thing at -2 here? Because look what happens whenever I put it into the function or the formula. F of x minus h, right? Well, how about f of x minus -2? What's that turn into? F x plus 2. And I'm sorry, these are cubes. See what happened there? Okay, now, that's one way to realize this. Now, realize when you see a plus 2, notice it's at -2. That's one way to look at it and go, anytime I see a plus, I know the x is going to be at negative. I didn't know it. Okay? Or you can always solve for 0. X plus 2 equals 0. Solve it, you get x is equal to -2. So this thing moved. When you see a plus symbol, plus moves to the left. Negative moves to the right. It does the opposite of what you want, okay? It's not always that way. For these, left and right, that's how these work, okay? Because these are inside the function, right? Remember, this is your base function right here, this x cubed. I replaced the x with the x plus 2. Okay, and so that tells me, hey, this still looks like my base function, but what do we do to it? We moved it to the left. We just took it and moved it. Good? You okay with that? Sorta? Practice it probably. It'll be one of the more confusing ones. Okay? Let's look at. Notice I'll give you a big caution. It's everything I just said, okay, but it's on your notes. Okay, it's what I talked about with the moving left or right. Vertical shifting, here's another function. Remember that one? Look at this one very carefully. We see our base function there. The base function is red. It's a fraction, right? Any fraction is going to look like that. Why is that doing that? Why do we have this? Tell me, just as a review, why is this happening? The red lines are never going to touch that yellow line. For what reason?
Restriction.
Restrictions. Remember, because if x equals 0, what happens right there? Can't happen. You have an undefined, right? Because you can't divide by 0. So notice you have, since it's an odd function, I know that I have one part going in this area, then one part up high. Okay. Remember, had that been x squared, everything's on top. Okay. These are the functions you learned the other day. You need to remember those. Okay. Trust me, they're gonna help. I promise you. Just the memorization of them is gonna help out. But notice on this one, there's my base function. I did nothing to it, right? That's still just 1 over x. My base function would just be this guy in the red. But then what did I do? I did a +3. And what happened to him? He literally moved up by what? 3. He moved up. Notice this one, when you see the plus symbol, you can really go, yeah, I can move it up. So if you saw a minus, you can move it back down again, okay? So the plus would obviously just mean move it up that many units along the y-axis. Can I do both? Can I move it to the left and right and then also move it up? Yeah, we're going to be doing that. Okay, like had there been like a 1 over x plus 2, notice x plus 2 would be telling you I'm going to be moving what direction, right or left? On down here, if I have it right here, if I have 1 over x plus 2 and then a plus 3. The plus 2 here tells me I'm going to move it, what, up or down or right or left? Right and left, okay. Am I going to go right 2 units or am I going to go left 2 units? Left, because remember when you see positive, you go negative. Because this part's inside the function. Now, after I've moved my left 2, then I'm going to do what? Up 3. Up 3, there you go. So I moved it, then I move it up. Okay, and it does help doing it that way, to be honest. Sometimes it does help doing the horizontal first. I'll give you some notes here about the way they tell you. I'll be honest, sometimes I do them backwards, but I've done a lot of these. Okay, whatever way works for you, once you learn it, now let me hear you. This is how you get good at math. When you learn something and you know you've learned it, don't change. I don't care who comes out of the woodwork, so hey, I got a trick for you. Just put your fingers in your ears and go la 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 la. If you've got a way that you know how to solve it, unless the way they show you is just like mind-numbingly easier for you, then go to that and learn. But once you find a way to do something, don't change. Stick with it. That's how you get good at it. It's going to other places and hearing like other things. Not saying my way is the best. If you look on YouTube, find a way to do it better. Okay? But once you got it, stick with it. Okay? That's how you're going to get good. We've moved left. We've moved right. Okay? Now, let's reflect. Okay? Reflecting is pretty easy. Now, in your notes, I do this a little bit differently because I kind of play with this one, and I'm going to play with it with y'all as well. But let me read this first, and then I'm going to kind of blow it up. Given a function, f of x, remember our red is always our base function. The square root of x will always look like the red. That's what it looks like. If I didn't do anything to it, there has not been any movement. We didn't plus or minus anything on the inside. We didn't plus or minus anything on the outside. We good? That's just the base function, what you learn to memorize. But then I start messing with things. The graph of the function g of x is equal to negative f of x is the reflection of the graph with respect to the x-axis. Or the graph of the function g of x is f of negative x is the reflection with respect to the y-axis. That looks a little weird. In other words, a function is reflected with respect to the x-axis by multiplying the entire function by -1. And is reflected with respect to the y-axis by replacing x with negative x. Okay, let me show you what all this says. First off, they give us the g of x. Okay? G of x is what you're seeing on number 2 here. Because notice what they said was inside here, inside the function, you get that negative. Okay? But look at this. We're going to reflect that guy off. That's the g of x. But let's make some new ones. What would happen if I have h of x and it's equal to, hey, the negative square root of x? Wouldn't that be a number 1? Right there, look at the number 1 right there at the top. It says, hey, wouldn't you just flip it across what? The x-axis at that point. So you'd have something that looks like this. And that's going to be your h of x. Kind of makes sense. If you plug in some numbers real quickly, it makes a lot of sense. Okay? Notice the square root of 4 is what? 2. But then I've got that negative sitting out there, right? So notice I could have come over here to 4 and then gone down, and I should have got a negative 2. If I had drawn it perfectly, it had a negative 2 there, because that negative is sitting on the outside of the square root. So it reflected it across the x-axis. Well, okay then. Let's do another function. What if I give you j of x, and it's equal to negative square root of negative x? Well, let's think about it. First off, we know when there's a negative on the outside, it's going to reflect it where? Across what axis? The x. But when there's a negative on the inside, it's going to reflect it across where? The y. So you've got a reflection of a reflection. Okay? Or this thing would now turn into, let's do it in gray, that guy there. And that's going to be my j of x. Good? So negatives will reflect things. Okay? Kind of makes sense. You all kind of knew this, believe it or not. You just didn't realize it. Because think of it this way. Whenever I gave you a parabola, if it was a positive parabola, it did what? It went up, right? Well, what happened to a negative parabola? It went down. That's exactly what happened. Okay? It just flipped. Okay? I don't want to just blow past this. I want you to kind of really, if there's a, if you need me to slow down or say, hey, what do you mean by that again? I'll go back. Let's look again, real quick. So, x plus 2 tells me I'm going to go where? Left or right? Left. X minus 2 cubed, I'd go where? Right, exactly. I'd come over here, and there would be my point, and then there would be my line. I'll draw it as I can. Good? That's happening whenever, notice, realize your base function, your f of x, I'm going to make this, let's just do this j of x here, is equal to the x cubed. All of this is what's happening right there. Okay, we replaced the x with this other junk. So since I know that is happening like kind of inside the function part, even though the whole thing's a function, but inside the main part of the function, okay, I know that's my left or right. Okay. Anything that's happening outside that, like this right here, there's a plus there. It's just plus 0. So I didn't move up or down. It's just not going anywhere. Okay. Now, anything I add onto that function now is going to be what? My horizontal, my vertical, right? My up or down. So on this one up here, we even looked at this one. If I decide to add a plus 1 here, what's gonna happen to even just this base function here? It's gonna go where?
Up one.
Up 1. It got moved up 1. If I add it to right here, this one goes up 1. Notice what's happening here. I'm just kind of moving it up. Okay? Same thing. Everything's gonna happen that way. What would this mean? Well, what would that mean?
Over.
Yeah, it looks like I would flip it, doesn't it? Look like I would turn this into, this one would turn into a. Would it just flip itself around, right? More or less? No, actually, it's hard to flip them like that. This is gonna be going up, so yeah, this thing would go, oh, I see now, yeah, it would go. Just flips it upside down, doesn't it? That's all that happens. Okay. Good? Okay. Let's keep going. Play with them. Go on to Desmos. Play with these. See what happens when you start messing with the numbers. Don't just do the math of this. Okay? Things are good. Desmos is going to become very important for you later on, I promise you. So the better you get at now, the better. Okay? But if you go in there and go, okay, here's my base function. What's going to happen whenever I put a 2 here? Oh, look what happened. It made it squish in. What happens when I add a plus 1? Oh, look, it moved up. Okay? Play with them. Learn them. Okay? Learn their attitudes of what's happening whenever you start adding numbers to them. All right, so we have left and right, up and down. We've flipped across all axes. Vertical stretching and compression. Vertical stretching and compression. Let f of x be a function and let a be a positive real number. Okay? Positive real because look what we're dealing with. We're dealing with a square root. Okay, I want to rewrite this one though because I really want you to start understanding what you're actually seeing. Notice you have the square root of x over 10, but that could also be written like this. F of x is equal to, how about 1/10 square root of x? Okay, remember you can pull that out, okay? So look what it says here. The graph of the function g of x equals a of f of x is stretched vertically, okay, compared to the graph of f by a factor of a if a is greater than 1. So if a is greater than 1, it's going to do what? Stretch it. It's going to start stretching that guy. It's not moving him up and down. It's taking that function and doing this to it. Pulling it like taffy. It's still going to do its attitude, but it's going to get a lot larger. Okay? But if it's less than 1, what's going to happen to it? And if it's between 0 and 1, can't have a negative because we're dealing with a square root. Okay? What's going to happen to it? Notice the graph. What happened to it? Squished it way down. It is 1/10 the size of the original function. It's squished it down to where it's almost touching that x-axis. Good? I was kind of thinking this one this way. Wider or skinny. Makes sense? Give me enough calories. It's gonna happen to me. I'm gonna get wider. Stretch me out. Cut my calories. I get skinnier. Hopefully. I've been working so hard. But I'm trying. Horizontal stretching. and compressing. This one, they didn't give you one, so I just pulled one out of Desmos. Notice my base function is the red. Okay? But then look at it carefully. The graph of the function g of x is equal to a of x is stretched horizontally compared to the graph of f by a factor of 1 over a if it's between 0 and 1, and 0 and 1 is not inclusive because you can't add, you're not adding the endpoints. Okay? The graph of the function g of x is equal to f of a of x is compressed horizontally compared to the graph by a of f by a factor of 1 over a if it's greater than 1. Well, look at this one carefully. What's our base function we're looking at? Just the very base plain Jane function. What is it? If you had to write it. F of x is equal to what?
X cubed.
Very good. It's x cubed. There's my base. Without doing anything to it, that's my guy. So this is my guy right here. That's what it looks like, right? But now I decide to do what? I'm going to go ahead and do what? Am I stretching him or compressing him? Let's look at the math here. Notice it says a of x. Well, I have f of x is equal to, well, sometimes saying x over 3 looks weird. So how about we just turn this into 1/3 x cubed? Well, is that less than 1? And if it's less than 1, what's happening? It's being stretched. Okay? Anything greater than 1, right? What's going to happen to it? Greater than 1, it's going to start doing what? I won't say shrink, compress. It's going to start doing this. It's going to get closer and closer to that y-axis, whereas the other one was getting closer and closer to the x-axis. Okay? Everybody understand the math I'm doing with that 1/3? Are you seeing how that's working? Okay. Can we all agree? What's the you see the x value? You see the x variable? What is the coefficient of that x?
1.
1. So what you're seeing is this: 1 over 3 times x over 1, which would equal x over 3. Okay. It's just sometimes I like to pull out and see the fraction is what I'm actually seeing. It's really up to you. Okay, start learning about some of that algebraic manipulation now. Okay, it'll help out. So we stretched, we compressed. Now, order. If a function g has been constructed from a simpler function, the simpler function, which I keep calling the base function, okay? I'm telling you right now, and I'll sound like a broken record and I don't care because I want you to pass. Look for the base function. See if you can just see what the base is first. If you're dealing with a cubic function, you know what it is. You know what it looks like. And then you can start going, okay, what's this guy, what's happening to this guy? First off, that's how it's going to be on your midterm. It's going to say, hey, identify the base function. Oh, look, I'm dealing with absolute value. There it is. Circle it. Then you go, well, what's happening to it? On your homework, what you're going to have to do is this. It's going to say, hey, take this, and you're going to see it not as the base function, but as another function. They're going to say, what happened? You're going to see the function up here. What are we doing to it? Okay, I'll show you on the examples. Horizontal shifts, left or right. Horizontal, vertical stretching and compressing. That's what's happening inside the function, right? If you're dealing with square roots, where's the x at? Okay. A lot of your compressing is going to happen with square roots of like your square roots, cube roots. That's going to be your compressing. Okay. Or like the one we just saw. The stretching part and compressing, that happens a lot with your functions that aren't contained within something. Reflections. Where's the negative at? Right? If there's a negative, it's flipping. Where's it at? Okay. Is it flipping across the x-axis? Is it flipping across the x-axis? Is it flipping across the y? Is it flipping across everything? Did we flip it and then flip it again? Remember how we did the other one? Okay. And then finally, vertical shifts, up and down. Something happening outside that simpler function, at plus or minus. And those plus or minuses we can trust. A +2 means we're going up by 2. A -2 means we're going down by 2. Okay? An example. Do a few examples here. Consider the following function. I give you both here. Determine the more basic function that has been reflected, stretched, or compressed. And then step 2 is identify the shape of the more basic function found in step 1. Okay? Well, notice this was pretty straightforward and simple. It says what the base function of this one is going to be a what? What is it? Look at step 1 of 2 says, what is the simplest function you're seeing here? They've done some stuff to that function, but what would be the base function? When we started learning in 3.3, what would be the function you're actually seeing right now? Exactly. Everybody see it okay? Sure. Yeah. Look, what you're actually seeing is n of x is equal to x cubed. Well, now we need to know, well, what does an x cubed graph look like? Notice it's not saying what does it do after what we've done to everything. What does the base function look like? Are you talking about this one right here? That one? Everybody agree with that? That's your guy there. Very good. Very, very good. Be real careful because it's easy to confuse this one with one. They're real close to each other. Both of those are cubes. It's just one is a cubic function. One is x to the power of 3. One is the cube root of x. Okay? So just be very careful. And that's how that part of the homework's done. It's not all that easy, but I want to show you one. Okay? Look at this one here. The basic graph of f of x is equal to x cubed is shown. Manipulate the graph of f of x to display the graph of g of x to give us a new function, where x plus 3 cubed plus 6. Okay, and my graph and drawing skills to do this is not going to be perfect, okay? What you're going to have to do on Hawks is you'll just grab that little blue dot there and drag it, okay? So, what are we doing first? Okay, we're going to move to the left. How do you know that? Exactly. Look right here. There's a positive 3 right there. That means we're going to take this guy moving how many units to the left? 3, exactly. So x plus 3 cubed plus 6 is going to be 3 to the left. Okay, so I grab this guy and go 1, 2, 3. So, okay, there's that guy there. I can't graph him yet, though, can I? I haven't moved him yet. Well, I'm going to move him. It has moved. If you were doing some Hawks, it would have already moved. Are we done? No, now what has to happen?
2, 5, 6.
Exactly. We're going to go up 6 because of this part right here. We know that we need to move up, okay, or positive 6. And in Hawks and some of these, once you hit like up, it's going to say what? It'll drop a box there and say how many plus. You don't have to put pluses, but if you have to go negative, put a negative in there, okay? So yeah, so we're going to come up here and go 1, 2, 3, 4, 5, 6. Here's my new deal. And then if Hawks was doing this for me, I would get a new function right there. And so that's what it did. We moved it to the left 3. And then we moved it up 6. Now, on this one, it's pretty straightforward and simple. You could have gone up by 6 and then left by 3. It's really up to you. But once you find a way to do it always. Okay? I am big and partial going left and right first, like they say to do. Okay? Do the horizontals first. Okay, let's do one that you're going to see in Hawks. Well, this is all these you see in Hawks. Let's see what they show you here. Now, the only difference is on this one is, of course, as I click these things on here, you're not going to see what's happening, but I'll kind of walk you through this. Notice we have a function p of x is equal to the -2 multiplied to the cube root of x minus 3 minus 1. Now, what is the base function? I give you a picture of it. What's the base function? Cube root of x, exactly. My base function is the cube root of x. Okay. Now we got to decide, what did they do to this thing? Okay. So the first thing I always do, especially when they look really, really bad like this, let's be honest, the cube root of x, the base function says, hey, let's look and see what's happening inside that cube root first. So what's happening? What are we going to do inside that cube root? What do they do? Look at it carefully. Inside, that's going to determine what?
Direct.
Which one? Vertical or horizontal? Horizontal, exactly. What's happening inside that function says whether I'm going to go left or right. So I'm going to go left or right. Right by how many units? You know it's right because it's a what? A negative, exactly. This is the one part where you're going to have to go, okay, when I see a negative, I'm going right. When in doubt, solve. X minus 3 equals what? X minus 3 equals 0, which is going to be equal what? X is equal to 3. We'll go over to 3. Okay, kind of help you out a little bit. Okay, so I'm going to be going to the right. So the moment you do this in Hawks, when you click here, there's going to be a box pop up over in this vicinity. And here it's going to ask you how many units. In this case, we moved 3. Okay. Vertical, shift, or compress. Did we compress at all? Yeah, look at it very carefully. Don't we have a, what's happening right there? Something is being multiplied to that function. Okay? The number is a whole number. Okay, that means it's greater than 1. So is the function going to get larger? Like more stretched out, or is it going to get skinnier? Skinnier? Greater than 1, what's happening? Stretch. We're stretching that function. We're taking that function doing this. Okay. We're not looking at that negative, just look at the 2. You're seeing that negative going, it's less than. No. Look at how that's red. Between 0 and 1, 0 and 1 not included, you're going to have something being compressed. That negative sitting out there does something else. Okay? And we'll get to that. Okay? So notice you have some stretching happening. Okay? And it's going to be stretched by a magnitude of what? Exactly. We are being stretched. Once you click stretch, you hit 2. If nothing was happening, make sure you hit the none. Trust me, I got a lot of red bars because I would just look and see what it did, and I skipped through there and didn't hit. It actually said I didn't finish a part. Okay. Now let's look at that negative. Do we have an x-axis reflection or do we have a y-axis reflection? Let me kind of go back up here so I kind of went off where you can't see the function. Very good. X-axis, because guess what? That negative is not where?
Inside the function.
Inside the function. It's outside the function. Since it's sitting on the outside, x-axis reflection. If it was on the inside, y-axis reflection. Hey, if you had both, what's happening? You get both reflections. Okay, but this one only has a negative sitting on the outside. Go back to parabolas. Don't let this be confusing to you. If you have a positive, if you have x squared, you get a parabola, right? Well, notice that's positive x squared, it's going up. Well, a negative x squared will go where? Down. Where did it flip across? The x-axis. Same thing. All these functions behave exactly the same when something outside force is acting on them. So notice we have an x-axis reflection, yes, and that's for that one, you just gotta put yes. Because we have something of the negative cube root of x. Do we have y-axis reflection? Yeah, so you can put a note there. And then do we have a vertical shift?
Yes.
How much?
1, 2, 3. No,
Vertical?
One.
Up and down.
One.
One down or one up?
Down.
Down, exactly, down. And then you would have a button come up, you just put a -1 in there. Okay, don't put positives. Remember, you don't show positives. It'll give you that very, have you gotten that stupid, I hate it when it happens, because I know I did something when it says, you don't need this symbol that you're about to use. I don't like that for one reason. How many of you seen that ever pop up on a midterm or an assessment? You do those on paper. I don't warn you going, I don't walk by your desk going, hey, you didn't need that. No, you so. And there we go. Now I'm gonna graph this. I'm not gonna go to graph it very well, just to be honest with you, because I'm a human. I mean, if I wanted to do some test points, I could, but we're not gonna do that. But notice we did move to the right, okay? Right by 3, so I would go this direction, 1, 2, 3. I would go down by 1. That's gonna put me there. I'm gonna have some stretching, okay? Now, to be honest, graph is kind of close to correct. I did use Desmos, okay? But then you'd have something that kind of looks like this, where you have this right here. Because I flipped it right across the x-axis and stuff like that. So that's more or less what it looks like. If you want to see the exact thing, go on Desmos and take a look. I give you one more. I think we have time to finish this. We'll do some pretty quick. Oh, determine the domain and range. Hey, what's my domain and range of this guy?
Infinity and to infinity.
Yeah. All real numbers for both, right? Okay. It's going to ask you that. Just look at the domain. What is my base function? Let's do this. We've got 3 minutes. Let's do this one pretty quick. What is my base function? What are we going to see? M of x is equal to what?
26.
Huh?
X squared. 1 over x squared.
Yes. No one said that, did they? Earlier before him? Okay. Did you say it? Oh, shit. Okay. Good job. Notice, look at the power. Here's a little hint. Look at the power. Where is it at? And that kind of helps you out. Or look at the graph. They're giving you the base graph right now, right? Now let's look at it very carefully. Hey, are we going to do a horizontal shift up or down? Or sorry, left or right?
Right. Left.
Left, because there's a +2. So when there's +2s, we go left, and it's going to put us at -2. So this is going to be left, -2 units. Are we going to have a vertical stretch or compression? Is anything being multiplied to that function right now?
No.
No. So, none. Is there x-axis reflection? Yes, there is. How do you know that?
Negative and.
Because of that negative right there. Well, if the negative was somewhere else, like inside that, right, then we would have to deal with that, right? Okay. Is there y-axis reflection? No. Is there a vertical shift?
Yes.
Where?
Down 2.
Down, -2. And so that would give you, now this one you gotta be careful with. I want you to show this, is what I want to show you this. Notice I'm gonna come over here, I'm going down by -2, then -2, so I have a point there. But realize my function is going to look like this. Can we all kind of get that kind of carefully? Now be real careful, because look, remember, it's never going to touch that line, and it's also never going to touch that line there. Okay, so realize you have another part here. Determine the domain and range. Well, domain is going to be what? Think about it.
Infinity to -2.
Mm-hmm. And
-2 to infinity.
but what's your range now? Oh, it's a little different, isn't it? Look, it's never going to touch this here, is it? So wouldn't it be from -infinity to what?
-2.
Exactly. So you gotta be careful with that. Okay. Realize your range does not mean you're gonna get something undefined. Your definition of undefined or restricted values only comes with your domain. But the only problem with this one is, if you get a -2, well, that just means I get 0 divided by 0. So is that okay? Can you do this?
No.
You can? Can you divide by 0? No, you still can't do that. Don't let me fool you. You still can never divide by 0, even though this function says, well, look, but my range says no, can't do it still, okay? Good on transformations? Okay, tomorrow we will do 4, 2, 4, 3, okay? And then we'll finish up 4, 3 and stuff on Monday or on Wednesday. And then we'll have about the last half of class to do any sort of review for the final if you want, or for the midterm if you'd like, okay? But you need to email me your questions beforehand, okay? If not, you just haven't heard the class. Okay, good? All right, I'll see you guys then.